Why, hello everybody. Today we're going to go on to section 13.5, which deals with equations of lines and planes. And I must say, this section is extremely important. We are going to be representing lines and planes throughout this course. So you want to make sure you do a superb job in understanding what you're doing and understanding why an equation of a line is the way it is and the way an equation of a plane is. Without further ado, let's get started. First thing I want you to say is, if you were going to draw a line in space, what would you need to draw that line in space? Well, first of all, you would need a point on the line, right? You'd have to show me, give me one point that's on the line. Maybe this point right there is on the line, okay? Secondly, to be able to draw that line, you need to know in what direction is that line going. Is it going this way? Is it going this way? Is it going that way? Is it going this way? Is it going up that way? Give me some direction that it's going. Maybe it's going like that, okay? And once I know a point, that's a point to get started, and the direction that it's in, then you could very easily draw the line. Okay, well, that's exactly what we need to do in Calc 3 class to be able to draw a line. We need a point, and notice, people, you've got to be, it's very, very specific. The parentheses mean that it's a point, right? This is the point x naught, y naught, z naught. That's the point that's in on the line, and the direction that my vector is pointing is vector v, which is given by a, b, c. So we actually can call that vector v if you want. So v is the direction that the line is going, and x naught, y naught, z naught is a point that's on that line. And if I went to draw the line, it would look something like that. All right? Now, to derive what the equation of this line should be in three-dimensional space, if you picked any point at all, some general point, and let's call this general point x, y, z. All right? Let's look at the vector that's going from the particular point that we know that's on the line to this general point, and let's draw it right here. How could I represent the vector that goes from x naught, y naught, z naught to x, y, z? It would be represented, and we know you subtract, final minus initial, terminal minus initial. So its x component would be x minus x naught, its y component would be y minus y naught, and its z component would be z minus z naught. Okay? All right, now, what do I know about vector ABC, this vector, and this vector that goes from x naught, y naught, z naught to x, y, z? Well, I think you could say those vectors are pointing in the same direction, aren't they? Now, granted, I could have picked x, y, z down here, in which case this vector right here would be pointing in that direction, but then this vector would just be in the opposite direction of that one. Now, when two vectors are pointing in the same direction, or if one's pointing in the opposite direction of the other, we say that those two vectors are parallel, right? And if your vectors are parallel, what do you know? That means you can multiply the one vector by a scalar and stretch it to match the other one. Notice, if this green vector was going in the opposite direction, the scalar would be a negative to be able to turn the direction and then stretch it. So we're saying, since vector x naught, y naught, x minus x naught, y minus y naught, z minus z naught is parallel to ABC, x minus x naught, y minus y naught, z minus z naught is parallel to vector A, B, C, then there's got to exist some scalar that I can stretch this one by, multiply it by, to equal the other one. There's got to be some number. Now, I could represent the scalar as K or C. For some strange reason, most Calc 3 books represent it as T. So I can find some scalar, oops, there's a comma here, comma, y minus y naught, comma, z minus z naught, so that if I multiply vector A, B, C by that scalar, this vector is equal to that vector. Okay, easy enough. And so therefore, x minus x naught, comma, y minus y naught, comma, z minus z naught is equal to A times t, comma, B times t, comma, C times t. Move that up so you can see it. All right, now, when two vectors are equal, this vector equals that vector, the only way you're going to get two vectors to be equal is to have their x, their y, and their z components all equal to each other. Therefore, x minus x naught must equal a times t. Y minus y naught must equal b times t. And z minus z naught must equal c times t. Okay? Or, if I want to solve for x, I could say x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus c times t. So, notice the equation for a line in three-dimensional space is given by not one equation, but a set of equations. Notice what's given here. Be able to determine this set of equations that describes this line in three-dimensional space. Notice, what's the x naught, y naught, z naught? What is that? That's the particular point that you know that's on the line. So x naught, y naught, z naught is a point that's on the line. And the a, the b, and the c is a vector that's pointing in the direction of the line. Notice, the x naught, y naught, z naught will be given, the a, b, c will be given, and notice, if you pick t to be one number, it will produce one point whose coordinates are x, y, z. You with me? Notice, if you let t be 1, you're stretching this vector 1 times this vector. So you're getting the point right here whose coordinates are right here. If you let t be 2, if I stretch this vector by 2, a multiple of 2, what do? I double it. So I'm going to get a vector I'm going to get the point that's right here, a distance 2 up here. If I make t be 3, I'm getting a point that's designated by 3 times that vector. Notice, a line is is one-dimensional, right? A line is one dimension. You can go to the left, you can go to the right. And notice we just have one variable in determining our points. Pick t, and the point is uniquely determined. All right, so in summary, a line goes through a particular point, x naught, y naught, z naught. It's in the direction of vector a, b, c. And all points x, y, z on the line will satisfy the following set of parametric equations. So it's not like you're back in, your Algebra 2 days where, the equation on the line was 2x plus 3y equals 6. That does not happen. In three-dimensional space, to uniquely describe a line, you need a set of 3 parametric equations. X equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. Now using those, let's practice a little bit. Let's do this one. Example, determine parametric equations of the line that goes through the point 3, 2, negative 1, and is parallel to the vector I minus 2j plus 3k. So first of all, I say to myself, I need a point. I need a particular point. So what's my particular point? My particular point, which is x naught, y naught, z naught, is 3, 2, negative 1. That's your x naught, y naught, z naught. That's a point that's on the line. Then I need a vector that's parallel to the line. And what is that vector? Its x component's 1, its y component's negative 2, and its z component is 3. Okay? And then all we have to do is plug in using the formulas that we had before. My first equation is going to be x equals, my x naught is 3, plus my a is 1 times t. Y is y naught, which is 2, plus b, which is a negative 2, times t. And, it's not too mature to write 2 plus a negative t, 2t. It probably would be nice to write 2 minus 2t, I guess would look prettier. And z is equal to z naught, which is a negative 1, plus c, which is 3 times t. Now here's my set of parametric equations. Notice, if you let t be 0, what are you getting? X is 3, y is 2, z is negative 1. You're getting the particular point that's on the line. If you let t be 1, you're stretching this vector by a length of 1. You're taking 1 times its length. If you let t be 2, you're getting a point that's twice the distance that that vector is. Not hard at all, is it? It's pretty easy. Very important, though, to have it down. And notice, the set of parametric equations has one variable. It's one-dimensional. When you give me a t, and x, y, and z are uniquely determined. All right. That's one way to represent the equation of a line. One way to represent the equation of a line is using this set of parametric equations. We have 2 more that we have to go over. Another way to represent the equation of a line is the vector equation of the line. All right, now I want to go over a little bit of what's a position vector. So let's do that first. If you're in 3-dimensional space, and you have some point, let's say x, y, z, up here in 3-dimensional space, there's the point x, y, z. The position vector denoting that point is the vector that starts at the origin and ends at that point. It's pointing out the point from the origin. And you guys can tell me, what are the components of that vector? Well, if this point right here is the origin, it's 0, 0, 0, right? And so this would be x minus 0, which is x, y minus 0, which is y, z minus 0, which is z. Okay? No big deal. We could call that vector r. And we could represent it as the position vector that's pointing out the point x, y, z. Okay, not too deep stuff. All right, now using that thought process, though, I have a particular point, and this little point right here is x naught, y naught, z naught, but the vector that's pointing me to x naught, y naught, and z naught is the vector whose components are x naught, y naught, and z naught. We all okay with that? I should have made x, y naught, z naught in red to go with the red vector. I'll do that next time. Okay? Now, looking at this, vector ABC is the vector that's pointing me to in what direction I'm going. Okay? Now notice, if I took, I'm going to call, just to make life a little bit easier, let's call vector r naught, I'll do it over here. Let's call vector r naught the vector that's x naught, y naught, z naught. We'll call him r naught. Okay? And I'm going to call this vector ABC. That's the one that's pointing me in the direction of the line. Let's call him vector v. Now, as we said before, we could take this, and we could take vector r naught plus vector v. And if we take r naught plus vector v, what are we getting? Now notice, when you add two vectors, what do? You draw the first vector, you draw the second vector where the first one ends, right? And your resultant starts where the first one starts and ends where the second one ends. This resultant vector is pointing me to this point. Now what if instead of r naught plus v, I took r naught plus 2 times v? If I was going to take r naught plus 2 times v, what would I do? I would draw the first vector. Then I would draw the second vector where the first one ends, but if I'm taking 2 times v, I'm taking twice the length of this vector, so it's taking me to here. And my resultant would start where the first one starts, ends where the second one ends, and it's pointing to this point. What if instead of 2 times v, I took 3 times v? What would it do? Draw the first vector, draw the second vector. Now if we go 3 times v, you're going to go 1 times 3 the length. It's pointing me to that point. This vector's pointing me, it's the position vector to that point. What if instead I took r naught plus a negative 2 times v? How would that make me go? In the opposite direction. You would draw r naught, which is right here, but then we would, let's get blue for a change. If we're taking minus 2 times v, we're going to go minus once its length, minus twice its length. The resultant starts where the first one starts and where the second one ends. It would be pointing that point. Do you realize if we multiply this vector ABC by, we would take a half of it. It would take me here. We could take 2.5 times it. It would take me 2.5 the lengths. So in other words, if we stretch and shrink and reverse it in the opposite direction, if we take r naught and multiply it times any length times vector v, and let t range over all the reals, we're going to be generating all the points on this line, up this way, and in the opposite direction if we let t be negative. And we can call represent all of those points as r. Are you all with me? Do you follow what I'm doing? Okay, so let's look what we're saying here. Let me just draw it one more time. If I have a vector, and we're going to call him x naught, y naught, z naught. Maybe he takes me right to here. That's a particular point on the line. X naught, y naught, z naught, and we call him r naught. That's taking me to a point that's on the line. Now let's pretend the line's going this way. If you give me one vector, which I'm going to call that vector ABC, when you add two vectors, you draw the first one, you draw the second one, and your resultant, since it's starting where the first one starts and ending where the second one ends, since this one's at the origin, it's going to be the coordinates of that point that you end. Now, as you notice, if we stretch, shrink, go in the opposite direction, if we take any different multiple of vector ABC, we will be generating all the points along this line. So r naught plus t times v is going to generate all the points on that line. So I'm going to write it as r equals r naught plus tv. Now notice r is just representing some particular point on the line. Some point on the line. So r is vector whose coordinates are x, y, z. r naught was x naught, y naught, z naught, because that was the particular point, plus t, and vector v had components a, b, c. Now notice, let's just do a little bit of vector algebra here. If we go x, y, z is equal to x naught, y naught, z naught, plus a times t, b times t, c times t. And when you add two vectors, what do you do with the components? You add them. So if I'm adding these two vectors, it's going to be x naught plus at, y naught plus bt, and z naught plus ct. Hey guys, look what we have here. If two vectors are equal, what do you know? The x components are equal. So x equals x naught plus at. Can you see that read very well, or is it too fine? You can see it okay? Let's use blue instead. Y would equal y naught plus bt, and z would equal z naught plus ct. It's equivalent to the parametric equation. Okay? But for the vector equation, if you give me a particular point and a vector it's in its direction, we will write our vector equation this way. Our general point r is equal to the particular point plus some multiple of the vector that's pointing us in that direction. And the way I think about it is, r naught tells me where to start, and then we're stretching and shrinking v to tell us in what direction to go. So our vector equation in general is going to be r is equal to the particular point plus t times v. r naught gives you your particular point, which in this case was vector x naught, y naught, z naught. And v tells us the vector that tells us in the direction that we're going. Okay? Not hard. Not hard. Now let's just do a couple of examples. Find a vector equation of the line that passes through 5, 1, 3 and is parallel to vector I, 4j, minus 2k. Now remember, we said the vector equation is given by r is equal to r naught plus t times v. r naught's our particular point. V is the vector that's telling us in what direction to go. So what is our r naught here? The line's passing through 5, 1, 3. So that's vector 5, 1, 3. V is the vector that's parallel to our line. That's going to be vector, now what are my components? 1, 4, negative 2. Okay, so my vector equation is r is equal to the particular point plus a multiple of the vector parallel to the line. So playing plug in for this, we're going to have r is equal to 5, 1, 3 plus t, and what's my vector that's parallel? 1, 4, negative 2. So, open this up. We have r is equal to 5, 1, 3 plus, and if I multiply t times each of these, I'm going to have 1 times t, comma, 4 times t, minus 2 times t, or r is equal to, when we add two vectors, we add the x components, add the y components, add the z components. Okay? Now, I think this is a beautiful way to write your vector equation. R equals this. Your book, if you look in the back of the book, remember, if you have vector phi, like here, you had vector I plus 4j minus 2k, and I wrote it in component form of 1, 4, negative 2. Your book, if you look in the answer to the book, they might very well write it this way instead. 5 plus t times I plus 1 plus 4tj plus 3 minus 2tk. And here is my equation in vector form. It's just like the parametric form, remember though, because R is the vector x, y, z, the x-coordinate, y-coordinate, and z-coordinate of the point. So yes, x equals this, y equals that, z equals that. Just a different way, and we've got to get comfortable with the two different forms. Okay, here's another one. Find a vector equation and parametric equations for the line through the origin and parallel to the line. So they want you to do it both ways. Why are they doing this overkill? Because we are going to be using lines all semester. So you have to know how to represent a line. You think a line is the most simplest form in geometry. So I say, okay, what's my particular point? Ooh, what's my particular point? What's x naught, y naught, z naught? To find the equation of a line, remember, you need to know a point that goes on the line and a vector that's in the direction of the line. In other words, a vector that's parallel to the line. So I go, okay, to get the equation of my vector, I need a particular point. Let's read the problem again. Find a vector equation and parametric equations for the line through the origin. So my line's going through the origin. So my particular point has coordinates 0, 0, 0. Now, they want the line to be, we want our new line to be parallel to x equals 2t, y equals 1 minus t, z equals 4 plus 3t. They're not giving us a vector parallel to our line. They're giving me a line parallel to the line. So let's just think about what's going on here. Maybe my line looks like this, and they're telling me my line has to be parallel to some other line. And I need a vector that's parallel to my line. Well, if I could find a vector parallel to the other line, wouldn't those two lines, both lines are parallel to both vectors, right? So can anybody get me a vector that's parallel to this line? What is a vector parallel to this line? Go back, and look here. Remember, in parametric form, what happened here? The x naught, y naught, z naught was a point that's on the line, but these coefficients of t, you see the coefficients of t there? The a, the b, the c, vector a, b, c was parallel to your line. So this line that they gave you, can you give me a vector parallel to this line? Aha! It's going to be 2, minus 1, 3. Take the coefficients of t for x, y, and z. So if I have vector 2, negative 1, 3 parallel to this line, and these two lines are parallel, this vector is also going to be parallel to that line, right? It's going in the same direction. So now I have a vector parallel to my line, and I have a point that's on my line. Okay? So a vector parallel to my line, I didn't spell parallel right, but you had the idea, is going to be, you guys told me it was 2, negative 1, 3. You want to do vector equation first or parametric equation first? I guess I'll do vector equation first because they asked that first, right? So for vector equation, it goes R equals initial point plus t times my vector. So R is equal to, initial point is 0, 0, 0, plus t, vector parallel, is 2, negative 1, 3. So R is equal to 0, 0, 0, plus 2t minus t, 3t. And you add those together, you get R is equal to 2t minus t, 3t. And that's my vector equation. And people, since R is the position vector x, y, z, I can get the parametrics right off from this, right? I mean, I could go back and use this. I could do that. You know, and plug in 0, 0, 0, and for x naught, y naught, z naught. And for a, b, and c, I can be plugging in 2, negative 1, 3. Or I can read it right off. X This x component is 2t, this y is minus t, and my z is 3t. How are we doing? We doing okay? Is it overkill or are we all right? Okay, all right, you with me? Now I could have also instead said x naught, y naught, z naught is 0, 0, 0, so you could put 0, 0, 0 here, and then put 2, negative 1, 3 in for a, b, and c. You'd get the exact same equation, the exact same equation. Okay, one more. Well, lots more than one more, but let's do the next one. Okay, I want you to understand something that's very important. Parametric equations of lines are not unique. You think about it. Looking back at this equation, for the parametric equations, you have to pick a point that's on the line, and how many points are on the line? Infinitely many, huh? How many vectors are parallel to your line? Infinitely many. If you tell me my vector's parallel, if you say my vector, here's my line, and you tell me, oh yeah, I'm telling you, Mrs. Strocko, 1, 2, 3 is parallel to the line. Well, then I guess if I multiply that vector by 2 and double it, I'd get vector 2, 4, 6. That's still parallel to the line, huh? I could multiply it through by a half. A half, 1, 3 halves. That would be parallel to the line also, right? So since there's infinitely many points on the line, you can have all different kinds of numbers for x naught, y naught, and z naught, and you could have infinitely many pairs for that a, b, c. Okay, so just because you look at one set of parametric equations and you look at another set of parametric equations and they look different, don't assume they're different lines. They could be the same line. Okay, just to give you an example, suppose my line goes through 3, 6, 1 and is parallel to 1, 2, 3. Remember, your equations are get the particular point, x naught, y naught, z naught, get the particular, the vector parallel, this is your a, b, c, and one set of parametric equations would be x equals, and putting this, there's my little cheat sheet if you need it, x naught plus at, let's see, my x naught is 3, and my a is 1. It would be y equals 6 plus 2t, you with me? And z equals z naught, which is 1 plus 3t. So that would be one set of parametric equations. Okay, notice what this set of parametric equations gives you. Let me just see what it gives you. What if I asked you on a test, and I do this a lot of times, give me 5 points that are on the line. They go, Miss Strocko, you only gave me 1. Why are you telling me to give you 5? You gave me 1. How can I get you more? I say, well, I don't know. I want 5. Can anybody tell me how I would get some more points that are on this line? Let your t be anything. If you let your t be 0, you're going to get 3, 6, 1. That's 1 point that's on the line. Let t be 1. If you let t be 1, x is 3 plus 1 times t. 3 plus 1 is 4. Help me if I add incorrectly. 6 plus 2 would be 8. And 1 plus 3 is 4. There's another point that's on the line. What if I let t be minus 1? 3 plus 1 times a negative 1. 3 minus 1 is 2. 6 minus 2 is 4. Y'all with me? 3 times a negative 1 is a negative 3. 1 minus 3 is a negative 2. I got 3 points that are on that line. So someone could use this point. And instead of 1, 2, 3, a vector parallel, they could use 2, 4, 6. My particular point is 4. My vector's y component's 4. My point is negative 2. My vector's y component parallels this one. Do these look alike? No, they don't. Are they parallel? Are these vectors, are these lines parallel? How could I tell? How can I tell that my lines are parallel if I'm looking at them and I'm wondering if they're parallel? We'll call this line 1 and we'll call this line 2. Line 1 is parallel to the vector 1, 2, 3. Line 2, did everybody see how I got that? My A, B, C? What's line 2 parallel to? 2, 4, 6. Are these vectors parallel? How can you tell if vectors are parallel? If you can multiply a vector by one number, a scalar, and generate the other one, and I can see I can multiply that through by 2. So since the lines have parallel vectors that are parallel to them, the lines must be parallel. But be careful because I can represent a line infinitely many times, infinitely many ways. Okay, good point. Moving along. In review, you already have this copied down, but I just think it's nice to pull it together. Parametric equation of a line is give me a particular point that's on the line, give me a vector that's parallel to the line, and we have to know this down cold. Should this be on our cheat sheet? Yes, but it also should be in your head so firmly that you don't have to look at your cheat sheet. Find parametric equations and symmetric equations for the line through the points 6, 1, -3, and 2, 4, 5. I need to get the equation for a line. We'll do the parametric first, if you don't mind. To do the parametric, I need a point on the line. Okay, so I need an x0, y0, z0. I have two. I have 2 points on the line, so I can use either one, doesn't matter. I'll use the first. If you want to drive me nuts, on the answer key for the test, I'll have to make one up for 2, 4, 5 also. You with me? There is no one unique parametric representation for a line. I also need a vector, which we call A, B, C, parallel to the line. They've got 2 points here. They've got 6, 1, -3, and they've got 2, 4, 5, and my line is going through those 2 points. How can I get a vector that tells me to go in the direction of that line? Well, wouldn't you agree that this vector is parallel to the line? Right, or I could make that vector also, right? So let's subtract. If we go from here to here, you go final minus initial. 2 minus 6, and make sure, this is where I messed up last time. 2 minus 6 is a -4. 4 minus 1 is 3. 5 minus -3 is 8. So, using this, x equals x0 plus at, y equals y0 plus bt, c equals z0 plus z0 plus ct. My equation is going to be x equals particular x coordinate minus 4 times t, y equals particular, which is 1, plus 3 times t, z equals -3 plus 8 times t. The way I remember to get the symmetric is I solve each of those for t and then just set them equal to each other. We could pull out what the formula is, this is what the formula is, and just do it that way too. But I find it just as easy to solve for t. Okay, so solving for t for each of them. The first one, that would give me x minus 6 over -4 is t. Solving this one for t, y minus 1 over 3 is t. Solving this one for t, z plus 3 over 8 is t. So symmetric form is, just set them all equal. X minus 6 over -4 is equal to y minus 1 over 3 is equal to z plus 3 over 8. And this is called your symmetric form. Okay, I think we did enough of that. Okay, if I continue? I see some people writing, so I'm going to wait a minute. Studio audience helps me slow down. Okay, ready to move on? Okay. Oh, I like this one. Find parametric equations and symmetric equations for the line through 2, 1, 0 and perpendicular to both I plus j and j plus k. So first of all, I say, okay, now, to get the equation for a line, I keep putting that away and I should bring it back, I need a particular point and a vector parallel. So I say particular point, I've got. The line's going through 2, 1, 0. So my x0, y0, z0 is 2, 1, 0. I've got my particular point. x0's 2, y0's 1, and z0's 0. But I need a vector. I need my line perpendicular to these two vectors. So I got one vector, I plus j. Notice I never worry about drawing to scale. I just draw two vectors. And I got another vector, j plus k, and my line's going to come down perpendicular to those two. How can I find a vector in the direction of that line? Cross product. Cross product gives you a vector perpendicular. Wonderful. So I can take the cross product of those two. So that's now notice I plus j, if I write it in terms of x, y, and z components, it's going to be 1i plus 1j plus 0k. And this vector right here is 0i plus 1j plus 1k. So we're taking the cross product of 0, 1, 1 and 1, 1, 0. So to take our cross product, we're going to go I, j, k. I'm going to put this one in across here, 0, 1, 1 and 1, 1, 0. And this is going to give me I times, now help me in case I mess up, 1 times 0 is 0 minus 1. I can do that. Minus j times, let's see, eliminate the row and column j's in, so I have a 0 minus 1 plus k times 0 minus 1. So this looks like it's minus I plus j minus k. So I have this vector, I'm going to write it as minus 1, 1, minus 1. Okay? And so therefore a vector parallel to my line, my A, B, C, is negative 1, 1, negative 1. So this is my x. So now my equations are going to be x equals x naught plus at. So I'm going to have x equals 2 minus 1 times t. Y equals y naught plus bt. So y equals 1 plus t. And z equals z naught plus ct. Z equals 0, which you shouldn't really write, but we'll do for right now, minus t. Okay, now people, I'm looking at my answer key because, you know, if you noticed, I like to put like my answers there in the bottom so I can just follow along and see if I did okay. The answer that I copied from the back of the book is x equals 2 plus t, y equals 1 minus t, z equals plus t. That's what they have in the back of the book, and this is what Mrs. Strocko just got. Do I get any credit? Am I right? Am I wrong? What do you think? We're saying 2 1 zeros on the line. But with this set of parametric equation, what is my vector parallel to the line? It's 1, minus 1, 1, right? Did I do this right? 1, minus 1, 1. Oh, minus 1 here, excuse me. There was a minus here. Oh, no, 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 no. The answer book had this. So it's 1, 1. There you go. Thank you. 1 minus 1, 1. Now notice they have 1 minus 1, 1 parallel to the line, and we had minus 1, 1 minus 1. Are both of these okay? Yeah. Sure, because remember you can multiply this darn vector by any scalar. So they're just multiplying it by a minus 1. We took A cross B, or maybe we took B cross A. They took A cross B. And remember, A cross B and B cross A are opposites of each other. So my point is this. You look in the back of the book and your answer's not just like those. Look at what vector you have parallel, what vector they have parallel, and reconcile if they're both parallel to the line. They're not going to have 25 different options. You know, you have to think a little bit. Now, to get, I like this, so we're going to keep this. To get the parametric equation, I prefer just solving for t. So solving for t for this first equation, I get x minus 2 over negative 1 is t. Solving the second one for t, I get y minus 1 is t. And the third one is minus z is equal to t. I just took each of these equations, the parametric equations that I had, and I solved them for t. I find this is the easiest way to get the symmetric form. And so my symmetric form is going to be x minus 2 over a negative 1 equals y minus 1 equals minus z. Answer in the back of the book, they multiplied through by a minus sign. That's okay. All right, we doing okay? Okay, we need to go on. But I'll wait. This is symmetric form. This is symmetric form. I don't know why they call it symmetric form. We'll talk in a minute what this even means at this point. Right now they just solve for t and set them equal to each other. This is my favorite form, parametric. We're going to use that a lot. Okay, we're doing all right? Moving right along. Is the line through 4, 1, negative 1, and 2, 5, 3 perpendicular to the line through negative 3, 2, 0, and 5, 1, 4? I've got two lines and I want to know if they're perpendicular to each other. Let's make best case scenario, all right? Let's pretend the one line looks like this and it's going through 4, 1. I always think pictures help you sort of think through what's going on here. 4, 1, negative 1, and 2, 5, 3. And let's pretend they're perpendicular. Well, that doesn't look perpendicular, but use your imagination. I'm off by a little bit. And that has points negative 3, 2, 0, and 5, 1, 4. Now this chapter deals with vectors. All right? So if I drew the vector from this point to this point, and I drew the vector from this point to this point, if the lines are perpendicular, what do you know about the vectors? They're perpendicular, because remember, to find the angle between two vectors, you just slide this little guy parallel till he goes tail to tail, and you can see they would be at right angles. Now, in last night's no, not last night's homework, 2 nights ago, or maybe 4 nights ago, because it's every other day, how can you tell that two vectors are perpendicular? Aha, brilliant, wonderful. Your dot product is 0. So what am I going to do? I'm going to find this vector. The vector from 4, 1, negative 1 to 2, 5, 3. How do I get its components? I subtract. 2 minus 4 is a negative 2. 5 minus 1 is 4. 3 minus a minus 1 is 4. Help me if I make a mistake, because that's where I make a mistake in my subtractions. 2 minus 4, 5 minus 1. I also copy points wrong down too. And 3 plus 1 is 4. And to find this vector right here, 5 minus a minus 3 is 8. 1 minus 2 is a negative 1. 4 minus 0 is 4. So if the vectors are perpendicular, the dot product would be 0. So I'm taking the dot product of negative 2, 4, 4 with 8, negative 1, 4. Negative 2 times 8 is negative 16. 4 times negative 1 is negative 4. 4 times 4 is 16. This is equal to a negative 4. Since it's not 0, they are not perpendicular. And if the vectors are not perpendicular, the lines are not perpendicular. Okay? What I like about this chapter is, you sort of have to think a little bit. It's not, how do you do that one problem? Think about what's going on. Okay. This is a nice one. Determine a vector equation for the line segment from 10, 3, 1 to 5, 6, negative 4. Now, the only thing that is different here is we've got 10, 3, 1, and we have 5, 6, negative 3. So I just sort of draw, I don't worry about putting it in the XYZ plane. You have to be too much of an art form. This is much quicker. And we want the line segment going from here to here. Now, the vector equation we did before, you went R equals R naught, which is your particular point, plus T times V. Okay, and now let me just show you something. If I did, maybe spaces right here, but let's pretend X, Y, Z axes are right here. Notice, this is your, this is your vector, forget that line there. This is your vector pointing out the first point that you know. And this is your vector, V, pointing you in the direction. And notice, if we just want all the points in between, from here to here, what do we let T range from? Well, to start right here, you let T be 0, right? And if you want to get one full length of the vector, you're going to let T be 1. You see, if I let T be a half, I'm just going half the distance. Let T be a third, I'm just going to about here. T be 3/4, I'm going 3/4 of the distance. So the only difference is just let T range from 0 to 1. That's the only difference. So we need a particular point. I'm going to make my particular point be 10, 3, 1. So I'm going to let my R naught be the vector 10, 3, 1. I need a vector V that's pointing in the direction of the line. What's vector V going to be? 5 minus 10, which is a negative 5. 6 minus 3, which is a negative 3. Negative 3 minus 1. It's a positive. Oh, thank you. I appreciate it. All right. 5 minus 10 is negative 5. 6 minus 3 is a positive 3. Negative 3 minus 1 is a negative 4. So my vector equation is R equals R naught plus T times V. So it's going to be R equals 10, 3, 1 plus T times negative 5, positive 3, negative 4. I'm going to get a little bit lazy here. It's going to be 10 minus 5 times t, 3 plus 3 times t, and 1 minus 4 times t. And there's my vector equation, but we're going to let just t range from 0 to 1 because we're going no length, which means starts at the initial point, and stretch it one full length, which will just take me to here, and we'll just be generating the line segment. Now, if you let t go from minus infinity to plus infinity, you'll get the whole line. Okay? All right, now we've done a whole bunch of lines. The only difference with this one, we already, in fact, notice this is the same problem. It says determine the parametric equations for the line. I already got it right here for my vector equation. Remember, this is x, y, z is r equals this. So I could say x equals 10 minus 5t, y equals 3 plus 3t, z equals 1 minus 4t. The only difference is, since we just want the line segment, we just let t vary from 0 to 1. And that'll just give me the points that are in between. Okay? So this problem here is the exact same problem, but just let your t vary from 0 to 1 to get the line segment. Okay, we've got a couple more things to do. We've got to learn how to do the equation of a plane. Again, don't be busy copying this down. We'll write the equation for the plane in a minute, but I just want to show you where it comes from. Okay, my assistant did a nice job and drew this for me on the computer. Let me just move it over to the middle so you can see it just a little bit better. Now, this is easy, and it's just so beautiful. This is like one of my favorite things in Calc 2, or Calc 3. Here's my plane. Okay, here might see my plane. X naught, Y naught, Z naught is a particular point on the plane. Somebody's telling you like 2, 3, 5 is on the plane. Okay, now think about it. Every plane in space has vectors that are perpendicular to the plane. Like here's my hand on my plane. I'm thinking of there's a vector, and you can use the word orthogonal, or you can use the word normal, or you can use the word perpendicular. They all mean the same thing. So in this particular case, this vector coming out of my plane is perpendicular to the plane. Now let me just bring a sheet of paper here. Let me just show you something here. Here's a plane, my sheet of paper. Here's a particular point that's on that plane. X naught, Y naught, Z naught. Now, I'm going to have my blue pen coming out. That's a vector perpendicular to that plane. Do you see, if I pick any point that's in the plane and I draw a line from that point to X naught, Y naught, Z naught, do you see I get a right angle? See that? If I pick another point, they still make a right angle. Do you see that? Turn it a little bit so you can see the right angle? Every single point that I take. Do you see the green line with the blue vector forms a 90-degree angle? You all with me? Okay, so back here. Here's my plane P. And here's some point right here, x, y, z, that's on the line. Vector ABC, that's this one here, and this vector are perpendicular. All right, now it's quite obvious to me that vector ABC is perpendicular to the other vector. Now wait a minute, this vector goes from the particular point x naught, y naught, z naught to some other point x, y, z on the plane. How do I represent that vector going from x naught, y naught, z naught to x, y, z? I subtract x minus x naught, y minus y, I don't want dot product, I want to say perpendicular, z minus z naught. Now if this vector is perpendicular to this vector, what do you know about the dot product of those two vectors? So I shouldn't have crossed it out. The dot product of those two vectors should equal 0. Let's take the dot product. A times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. Isn't that beautiful? That's the equation of the plane. That's all you need. The A, the B, and the C, the A, B, C is a vector perpendicular to the plane. The x naught, y naught, z naught is a point that's on the plane. Now I have it typed up to look prettier, so let's pull it up. So if I put sheets on front, so let me find where it goes. Right there it is. A times x minus x naught plus b times y minus y naught plus c times z minus z naught is, I should say, instead of the equation, I should say an equation of the plane that goes through the point x naught, y naught, z naught. This is the point on the plane. With normal vector, what does the word normal mean? Perpendicular. Or orthogonal means the same thing. Orthogonal, normal, perpendicular, synonyms. Why do they have to have 3 different words for one thing? I don't know, but we better be able to understand all 3. The normal vector is ABC. So when you want to find the equation for a plane, you need a particular point, x naught, y naught, z naught, a particular point that's on that. And then you have to find one vector, A, B, C, that is perpendicular to the plane. In which case, A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0 because why? The dot product of this vector and that vector is 0 because they're perpendicular. Okay, now just do a couple. Find the equation of the plane through the point, 4, 0, negative 3, with normal vector A, j plus 2k. So I go, oh, piece of cake. This is my equation. So I think I'll just put this right up here for me to follow. And I think I'll fold this paper. It's exercise 24, page 866. Unless the addition changed, then you know you have to deal with it. Okay. All right. So I go, okay, I need my particular point. My particular point, x naught, y naught, z naught is 4, 0, negative 3. There's my point. So x naught's 4, y naught's 3, or 0, z naught is negative 3. And I need a vector A, B, C perpendicular. Normal vector means it's perpendicular, but what are its components? What's the I component? 0, j is 1, 2. So my equation is A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. So A is 0, so it's 0 times x minus 4 plus 1 times y minus 0 plus 2 times z minus a negative 3 is plus 3 equals 0. So let's see, that dies because it's times 0. That's going to be y plus 2z, 2 times 3 is 6, equals 0. There's my equation for my line, or my plane. My plane. Notice, in general, if you take this equation, A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. Note, please, that x naught, y naught, z naught are numbers, right? A, B, C are numbers. If you multiply it out, you're going to get A times x plus B times y plus C times z. And all these, if you multiply out, you can combine together to make it be D. So a lot of times your equation of your plane looks like that. AX plus BY plus CZ equals D, as we had in that. Okay, find the equation of the plane through the point negative 1, 6, negative 5, and parallel to the plane, x plus y plus z plus 2 is equal to 0. Now let's talk for a second. We're saying the equation for a plane can look like A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. But I said if you multiply it out, all these A times x naughts, B times y naughts, C times z naughts are numbers. They collect together to give you D. What do the coefficients of x, y, and z give you? What do those coefficients of x, y, and z give you when you lift them off of your equation for your plane? What do they give me? They give me a vector perpendicular to the plane, huh? So if I said I had a plane 2x plus 3y plus 5z plus 82 equals 0, can you give me a vector perpendicular to that plane? 2, 3, 5. Can anybody give me a point on that plane? A point on the plane. If I wanted to get a point that's on that plane, see if we ask things that you didn't think about. I give you that equation for that plane. What if I want to let y be 0, z be 0? What would x have to be? Negative 41, right? That's a point on the plane. It satisfies the equation. You see that all I did is let, I mean, I could let z be 1 and y be 1 and then figure out what x has to be. You follow? You just have to find a set of coordinates that satisfies that. Okay? Notice, people, let me just show you before I go on. And then we'll go do that problem I said I was going to do. Notice, with this equation that I just threw up on the board, notice, if you solve for z, how many choices do you have to make to figure out what the z-coordinate is? 2. A plane is 2-dimensional. Back here, when you got the equation for your line, how many choices did you have to make to figure out what the z-coordinate was? 1. A line is 1-dimensional. Okay? All right, now let's do the problem. The problem here is exercise 28. Find the equation of a line through the point. So I go, well, yeah. The point x naught, y naught, z naught, Mrs. Strocko, is -1, 6, -5. But they're not telling me a vector perpendicular to my plane, which is what I need. Instead, they're telling me that it's parallel to this plane. Now note, if you've got one plane and it's parallel to another plane, what do you know about the vectors that are perpendicular to those two planes? They're parallel. So a vector perpendicular to this plane will be parallel planes have the same normal vectors. Parallel planes have the same vectors that are perpendicular to them. So what vector is perpendicular to that plane? 1, 1, 1. So therefore 1, 1, 1 will also be perpendicular to my plane. So now I'm ready to go. My equation is going to be a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So it's going to be 1 times x minus a -1 is +1, plus b, which is 1 times y minus 6, plus c, which is 1 times z plus 5 equals 0. So let's see, I have x plus 1 plus y minus 6 plus z plus 5 equals 0. This is where I'm talking about connecting those. So I have x plus y plus z, 1 minus 6 plus 5, oh, is 0. So there's the equation for my plane. Can anybody give me a point that's on that plane other than -1, 6, 5? Give me another one. 1, 1, 1? Nuh-uh. If you put in 1, 1, 1, 1, 1, -2 is great, because if you put a 1 in here for x, a 1 in for y, a -2 in for z, we've got 0. Can anybody give me another point that's on that plane? 1, -2, 1. How about, that's perfect. How about 0, 0, 0? Okay, good job. Okay, let's move on and do another one. Find the equation of the plane through the origin and the points 2, -4, 6, and 5, 1, 3. Put a star by this. They're giving me 3 points that are on the plane. One is the origin. Another one is 2, -4, 6. And another one is 5, 1, 3. As you notice, I didn't even worry about drawing the xy axis. I just sort of put them on my flat. I'm assuming that my paper just goes through. It's the plane that goes through those 3 points. Okay? Makes it quicker to draw the picture. To get the equation for a plane, what do you need? To get the equation for a plane, if you go back and think about it, you need a point that's on the plane and a vector perpendicular to the plane. That's all you need, right? So I say to myself, okay, I need a point on the plane. You know which one I'm going to use? The origin, right? 0, 0, 0 is definitely the easiest one to put in. So that's my x naught, y naught, z naught. Now I need a vector perpendicular to the plane. Any suggestions? They didn't give you any vectors. They just gave you 3 points.
You can just find the vector in between 2 and then get the one perpendicular to that.
How are you going to do that?
Cross product.
Oh, fabulous. You can find this vector, you can find this vector, and you're going to take the cross product. This vector is 2, -4, 6. This vector is 5, 1, 3. All right? And to get a vector, because how did I know it was 2, -4, 6? Because you're taking 2 minus 0, -4 minus 0, 6 minus 0. Origin's a nice point to have. So this vector is 2, -4, 6. This vector is 5, 1, 3. We get a vector perpendicular to those two vectors? By taking the cross product. So we want to take the cross product of 2, negative 4, 6 with 5, 1, 3. And you've done a million of them where you've gone I, J, K, and put in 2, negative 4, 6, 5, 1, 3, right? Blah, blah, blah. Okay, let me show you a little trick here. Taking out my little TI-92 that I told you that you can rent from me if you want. I'm going to turn it on. All right, and I'm going to hit catalog. Because I always forget where it is. So if I hit catalog, excuse me, catalog is shift catalog. So I better hit shift catalog, all right? And then I'm going to come down, let me make it a little darker so I can see it. Maybe a little lighter. A little lighter would be better for me. Here's my catalog, and I'm going to go up till I see cross prod. Well, I have to go down, no. Okay, I got to see it so I can see it. Okay, coming up here, moving up. There it is. Right there it is. See? Cross prod. Okay, now they don't have my monitor here for me, so I can't really see because of the lights, but I'm going to hit enter. All right, and then we're going to do brackets. Shift bracket, because brackets are right here. Shift bracket. And the points are 2, negative 4, 6. So I go 2, comma, negative 4, comma, 6. Then I have to close the brackets. Then another comma, and then another bracket, and then 5, comma, 1, comma, 3. Close the bracket, and then I need to close the parentheses and hit enter. Okay, and can you guys read it? Because I can't. What is the vector? It's negative 36. Oh, I have 2 times. I can pull that up. Let me just hit shift end, and I can get rid of the 2. Okay, there you go. Now it's not 2 times cross product. What is it? It's negative 18, 24, and what was the third one? 22. Okay, so that cross product you guys just told me was negative 18, negative 18, 24, and the third was positive 22. Okay, sounds good. So now we have, this is the vector, this is my A, B, C. All right, and my point on the plane, we said we would use 0, 0, 0. So it's A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. So it's going to be a negative 18 times x minus 0 plus 24 times y minus 0 plus 22 times z minus 0. So it's going to be minus 18x plus 24y plus 22z is equal to 0. Okay? Now, if you look in the back of the book and they've multiplied through by a negative 1, are you okay? If you look in the back of the book and they've divided through by 2 and they have minus 9x plus 12y plus 11z equals 0, are you going to be horrified? No, they're equivalent, right? Okay. Moving right along, I have a couple more I want to look at. 2 planes are parallel if their normal vectors are parallel. We just said that. If you've got this vector, and you look at their perpendiculars, at their normal vectors will be parallel in the same direction. Nice thing to know. How am I going to figure out the angle between 2 vectors? Well, notice when your vectors are parallel, when your normal vectors are parallel, what's the angle between them? 0, right? They're 0. This is going this way, that's going that way. If you slide him up here, there's 0 degrees between them. We're going to define the angle between 2 planes is defined by the angle formed by their normal vectors. Now, when we were doing it before, if we had 2 vectors, A and B, how did we find the angle between them in our homework a couple nights ago? Dot product. Remember, we said A dot B was the norm of A times the norm of B times the cosine of the angle between them, and then you solved for the cosine of the angle between them and took inverse cosine. So it's the angle between 2 vectors is the angle between their normal vectors. If I give you 2 planes, x minus 2y plus z and 2x plus y plus z equals 1, and I want to get the angle between these 2 planes, what are you going to do? This is plane 1. What vector is perpendicular to that plane? 1, negative 2, 1, right? I'm just taking the coefficients of x, y, z. For plane 2, what vector is orthogonal or normal to it? 2, 1, 1. Right? 2, 1, 1. So since the angle between two planes is defined as the angle formed by their normal vectors, to find the angle between these two vectors, I'll call this vector A, I'll call this vector B, and I'll say A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Now A dot B I can do pretty easy. It's 1 times 2 is 2. Negative 2 times 1 is negative 2. 1 times 1 is 1. So it looks like I get a 1 there. Okay, how do I get the magnitude of A? How do we do that? Vector A here was 1, negative 2, 1. How do we get its magnitude? Square root of x component squared plus y component squared plus z component squared, so it's just square root of 6. How do we get the magnitude of vector B? Same thing. 2 square root of 2 squared plus 1 squared plus 1 squared, square root of 6. So we have 1, which is A dot B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So square root of 6 times square root of 6 is 6. So I have 1/6 is the cosine of the angle, or the angle is inverse cosine of 1/6. To save me some time on the calculator, if you do that in your degree mode, take my word for it, 80 degrees is the angle. Okay, no problem. We're going to skip this for right now. Oh, no, let's do it right now. I can do it quite quickly. Find the symmetric equations of the line of intersection of the plane. These are two planes. You take your, this is one plane. Here's another plane. Planes intersect in what? What do the planes intersect in? A line. So I have one plane is like this, and maybe the other plane is going off like this. And there's some line that's common to both of those. And I want to get the equation of that line. Okay, now there's multiple ways to do it, but I'm going to show you one way that we can use this particular section. Can anybody give me a point that's on that line? Can anybody give me a point that's on both of those two planes? In other words, if the line is the intersection of the two planes, I need a point that's common to those two. Just by looking at the equations and playing with it, can you come up with a point that's on both of those lines? Perfect. Point that's on both planes, and therefore on my line, is 0, 0, 1, right? Because 0, 0, 1 satisfies the first, 0, 0, 1 satisfies the second. Okay? Now I also need to get the equation of this. We're not going to do symmetric just yet. I need to get a vector parallel to my line. Right? A vector, some vector that's parallel to my line. Now, since this line is in this plane, do you notice since the line's in the plane, the normal vector will be perpendicular to the line, right? And since the line is also in this plane, the vector that's perpendicular to this plane will also be perpendicular to that line. You with me? Since L, my line, L, is in the first plane, L is perpendicular to the normal vector that's perpendicular to the first plane, but what's the vector perpendicular to this plane? 1, negative 2, 1. Do you see that? Because L is in this line, since L, is in this plane, the vector that's perpendicular to the plane will be perpendicular to the line. But the vector that's perpendicular to the first plane is 1, negative 2, 1. Now, this line is also in this vector, in this plane. So therefore, the vector that's perpendicular to plane 2 will be perpendicular to that line. So L is also perpendicular to 2, 1, 1. So if L is perpendicular to this vector and L is perpendicular to this vector, how can you get the direction of L? The cross product. So if I take 1, negative 2, 1 and cross it with 2, 1, 1, which we did a few minutes ago, if I can find my paper. You guys probably have your notes better than me because I just threw it out. We just did it on the calculator. We took the cross product of those two vectors. What did I get?
We didn't do that one.
We didn't do that one? Well, I'll do it on here then. Pop it on. You guys just have to help me with my numbers when I see it. Turn it on. I'm going to go second catalog. I'm going to hit, oh, I got cross product right down there already, so I'll just hit enter. Okay, and I've got to go bracket 1, comma, negative 2, comma, 1, close bracket, comma, bracket, 2, comma, 1, comma, 1, bracket, parentheses, and you guys tell me what it says. What does it say? Negative 3, 1, 5. Okay, so now I have my ABC, which is my vector parallel to the line, and my point on the line was, you guys helped me and said it was 0, 0, 1. The symmetric form, if you remember, went x minus x naught over A equals y minus y naught over B equals c minus z naught, z minus c naught over c. So it's going to be x minus 0 over negative 3 is equal to y minus 0, which is y, over 1 equals z minus z naught, which is 1, over 5. And there would be your symmetric equation. Okay, we just have a couple two that I just want to point on. I'm not, oh, don't take notes on this. Let's just follow for a second, okay? One last thing, and then we will call it quits. This is the last problem, promise. If it's not, it will be. Now, one last thing, and this one you definitely will want to put the grand finale in your cheat sheet. This is cool, though. Watch here. Suppose I have a plane, and somebody gave me the equation, and I have some point x1, y1, z1 that's popping up there in space. And I want to determine the distance, the perpendicular distance from that point down to that plane. All right? That's what the problem that we want to solve for right now. Again, don't be frantically copying this. Just follow and enjoy the show. Now, look what happens here. I want to figure out the distance from this point to the plane, perpendicular distance. So I've got a point sitting up here in space. I want to drop the perpendicular down to the plane, and I want to find out what that distance is. Now, with the equation ax plus by plus cz plus d equals 0, I know that vector ABC is perpendicular to the plane. Okay? So if I could take the projection, if I could find some point x naught, y naught, z naught on the plane, and take this vector from the plane to the point that I want to find the distance down to the plane, if I could take the projection of this vector onto vector ABC, do you all see that this distance and this distance are one and the same, right? All right, now just follow, but don't frantically copy it down. Do you all agree that if I have a right triangle right here, here's my right angle right here, here's my angle, if I knew this length right here, which I call the hypotenuse, this piece right here would be the hypotenuse times the cosine of the angle, because it's the adjacent side. So if I could take the length of this vector times the cosine of this angle, it would give me this length right here. You all with me? Okay. Now watch this. This is pretty cool. But don't copy it down. Just follow. Let me cover this up. So, this distance, which I think you have down. Oh, let's fold this a little bit so you can see it a little bit better. This distance from here to here is the same as this distance from here to here, which is going to be the length of this vector, which means the magnitude of x1 minus x naught, comma y1 minus y naught, plus z1 minus z naught. That's that vector, times the cosine of that angle. But now if I wanted to, I'm going to multiply by a form of 1 of the length of vector ABC over the length of vector ABC, see, because they would cancel each other out. But when you take the length of a vector times the length of a vector times the cosine of the angle between them, that's equivalent to the dot product. So that's really x1 minus x naught, y1 minus y naught, z1 minus z naught, dotted with ABC. All over the length of, this should say the length of ABC. She made a typo. That should be the length of ABC right there. Okay? Now, if I take the dot product of those two vectors, what do I get? I get x1 minus x naught times A, y1 minus y naught times B, z1 minus z naught times C, which gives me that for my distance. And if I multiply that out, I get A times x1, B times y1, C times z1, and then I have this minus A times x naught, minus B times y naught, minus C times z naught, all over this. Okay? So I go, oh, that formula doesn't look too good right now. I don't think I like it. But, going back to the original picture, x naught, y naught, z naught is a point on the plane. So since x naught, y naught, z naught is a point on the plane, it satisfies this equation, which gives me a times x naught times b y naught plus c times z naught plus d is equal to 0, because it's a point on the plane. So therefore, d is equal to minus a x naught minus b y naught minus c z naught, which if I factor out a minus, so d is equal to this. But guys, that's exactly what I have here. I have minus this. So minus this is equal to d. So the grand finale is the following. If you have a point, x1, y1, z1, and it's floating above a plane, and the equation for the plane is ax plus by plus cz plus d is equal to 0, and you want to compute the distance from that point, the perpendicular distance from that point down to that plane, that distance we have just derived is you take x1, y1, z1 and plug it into the equation, and then just divide by the length of the perpendicular vector. So do you have to derive it every time? No, 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 no. You want to put this on your cheat sheet. It's worth having it on. So for the grand finale, here we go. The distance from point x1, y1, z1 to the plane ax plus by plus cz plus d equals 0 is, you need to make it an absolute value because distance is never negative. And you're just plugging x1, y1, z1 into that equation. Take the absolute value of that, and in the denominator, you're taking the square root of a squared plus b squared plus c squared. Okay, so we're going to do one real quick. If I wanted to find the distance from 3, -2, 7 to the plane 4, -6, 4x minus 6y plus z equals 0, using this equation, all right, plugging that in, let me just fold this back so we don't have that taking it up. All we have to do is we're going to have absolute value of 4, plug 3 in for x, minus 6, plug -2 in for y, plus z, which is 7. Oh, and this should be, except, wait a minute, we have to, they were a little bit clever. We have to have it equal 0, so we got to change this equation to minus 5 equals 0, because you have to have equal 0. So it's minus 5 all over the square root of, your a is 4, so it's a squared, plus b is 6, so -6 squared is 36, plus the coefficient of z is 1, plus 1 squared, equals, and let's see, 4 times 3 is 12, plus 12 is 24, plus 7 is 31, minus 5 is 26, all over the square root of 16 plus 36 plus 1 is 53. And we're done. Okay? Your homework, I want you to read over this section, pages 858 to 865, and then we want to do problems 3, 5, 7, 11, 13, 17, 23 to 33, the odds, 47, 49, 53, and 65. Okay, and I'll see you guys next time. Thanks so much.